Okay, so thank you very much for having me here. I would like to tell you about the issues of solving blockchain scalability and privacy with cryptographic proofs of computational integrity. So let's start with the first slide. So let's talk a bit about inclusive accountability and why it leads to scalability and privacy. Let's move to the next slide. So here's a paradox. So Bitcoin was launched in 2008 and Ethereum was launched in 2015. So how come they are so slow? How come they can process only something like, 10 payments or even less per second, whereas much older systems that are based on technology from the 1970s, like banks and credit cards, can process, 1,000x more. So that's a paradox, right? So let's answer this. Let's go to the next slide, please. So the conventional model in which most of the world operates in is that of trusted parties like banks. And if you ask, how is it that we can trust this system? Well, we delegate the process of verifying integrity and making sure that everything is okay. We delegate it to lawyers, accountants, auditors, regulators. So we put our trust in some select group of individuals selected from society, and they are the ones who check that everything's okay. So that's how the conventional system works. So blockchains work very differently. They offer inclusive accountability, which means everyone is invited to be included in being sort of an accountant and checking that everything's okay. So the way this happens right now is that each and every transaction that happens on the blockchain should be verified by each and every one of us. We are invited to inspect all of them. If we run a node of any blockchain, that is what we are doing. So it's a beautiful principle. Verify, don't trust. Let's please move to the next slide. But however, it sacrifices two things. Clearly, it sacrifices privacy because now everyone sees all transactions, but it also sacrifices scalability. And let's see, that's a more delicate matter. Why is this the case? What happens is that if we want to, let's say, increase the throughput of any one of these blockchains by a factor of 10x, so there are computers in the world that can support this, and you could have a connection that can process, that much information. However, it won't be as inclusive because probably you and I'm using my laptop. That's what I have. I want to run a bunch of other things on it. This won't be enough. I would need to buy some bigger computer and then a bigger computer and move to some fiber optic and have an operation that sits on some data center. And very quickly, as we increase the scale of the system, it would become exclusive again and would pretty much fall back to the good old world in which there's a small set of highly trusted parties. And indeed, some of the blockchains that do profess, doing 10,000 transactions in a second and so on, they are comprised of a small number of very, very strong nodes. And that's okay, right? If you trust those nodes, that's okay. But really, blockchains at their core, they offer this beautiful principle of inclusive accountability that limits scale and completely eliminates privacy. So let's move to the next slide. And the amazing thing is that these beautiful protocols that were initially invented in the 1980s and became practical over the past 10 years or so, cryptographic proofs that prove computational integrity can solve both of these problems, both the privacy and the scalability. So let's move to the next slide, please. So let's talk a little bit about computational integrity and how we can have different methods for solving this problem or achieving it. So integrity. Here's a very nice story for children, highly recommended, called The Empty Pot. It tells about a Chinese emperor who wanted to select an heir, right, the next in line, and he had no children. So he summoned all the children in the kingdom and told them he's giving each one of them a seed. The child was instructed to put the seed in a pot and water it every day. And on the first day of spring, they should all come back. The child with the most beautiful flower will be the heir. So what happens is that all the children of the kingdom come back. They all have amazing flowers. But for one child who carries an empty pot. The end of the story is that that child is the one selected to be the heir. And the reason is that the emperor has given all the children barren seeds that cannot flower. And only this one child operated with integrity and did. So let's move to the next slide. As C.S. Lewis, the author, defined it, integrity is the property of doing the right thing even when no one is watching. So the child in the story operated with integrity, and integrity is an extremely important property to have. Let's please move to the next slide. And computational integrity is something that lets us, know that a computation has executed exactly as if we would have run that computation, right? And that's something very important. We would love it to be the case that all of our financial transactions, all of our, the forensic data, the health data is handled with integrity. And that's exactly the problem that is solved either in the conventional way by trusting someone to operate with integrity or by some other technology. So in this slide here, I put down, and by the way, I'll share all the slides later on so you can look at it at leisure. There are a lot of numbers here. I want to say that there are 5 different technologies that deliver computational integrity, that let you know that some program that was executed correctly. The first one, the simplest one, is naive replay. It means everyone just reruns the same computation. This is the way you check, sometimes a grocery bill or a restaurant bill. You just redo the computation. It's a very old method. It's very good, but it doesn't scale very well, and it completely eliminates privacy. It is also the technology that is used currently by blockchains, right? Everyone is verifying and not trusting anything. So that's naive replay. You have delegated accountability. This is this very old method that has been used by banks and, by us. When we think about banks, we delegate the accountability to someone else. There's a new technology, cryptographic one, called a trusted execution environment. Things like Intel's SGX, the trusted platform module, the TPMs of 10 or 20 years ago. And here your trust is in a piece of hardware. Think of it as something that is completely closed and you cannot open and see what's inside. And inside there's some chip that runs everything correctly with integrity and then signs with a secret key that's inside that hard shell, and no one can see what's inside. It signs that the computation was done correctly. And now your trust is basically in the hardware manufacturer, and your trust is in the inability to open up that shell and take out the secret key. So that's also the weakness of that thing, that once the shell is open and you can extract the secret key, then all of the integrity goes away. Then you have validity proofs, or proofs based on cryptographic protocols, such as our technology, and that's what I'll spend most of my time on. And there, we'll talk about it in a minute, but there's a reason why it has this green bar all around. I think it's pretty secure, and I'll explain why. And you also have another thing very popular in the context of blockchains, which is fraud proofs or optimistic rollups, where anyone can advance the state of the system, but you provide enough data for everyone to call out and say, hey, wait a second, someone did something incorrect. And then there's sort of some binary search to see who's right and who's wrong, whether the system was advanced with integrity or without it. So that's a different means. And in my view, it's not as good, but it's some other technology. So I mentioned there are 5 different technologies, all of them aiming to give you the same goal. And the goal is integrity, to know that people have been doing the right thing, even if no one is watching them. So let's please move on to the next slide. So as I hinted in the previous slide, I think our technology based on cryptographic proofs, and in particular on a zero-knowledge Stark, and I'll open the acronym in the next section, is one that is very viable in the context of blockchains. So let's please move to the next slide. So let's say again, what is a computational integrity statement? There is some statement that a party is making saying, I ran a computation correctly with integrity, and here's the output. So for instance, a grocery or a restaurant bill is a proof of integrity. It is checked or verified by naively replaying the computation. So here you can see an example of a proof of integrity in which the prover is the restaurant owner and the verifier is the customer. And the way verification is done is by repeating the computation. And what you get from this is knowledge or trust in the correctness of the statement. That the statement is you should pay $89.50. So let's move to the next slide, please. Now, ZK Starks give you also something that delivers the same effect. You get comfort that a statement is correct. But there are several very important differences here. First of all, you can have zero knowledge, meaning that the receipt, if you want, or this grocery bill, you can imagine it having some parts blanked out, and you would still know that the computation was done correctly and the output is correct, which sounds a bit mind-boggling and impossible, but that's one aspect that you can have. Another one, so that's the acronym ZK. The second property is scalability, which is really, really important, and most of my talk is going to talk about that aspect. So what does scalability mean? It means two things. First of all, verifying the correctness of a proof is exponentially faster, or logarithmic, same thing, in the length of the native computation that is being asserted. So instead of rerunning the computation, to check the correctness and integrity, you need to run something that scales like the logarithm of the running time. So you get this very dramatic savings in verification time. And simultaneously, the time needed to generate the proof doesn't explode. It scales quasi-linearly, or like t times polylogarithm in t, where t is the number of steps of your computation. So that's another aspect that a ZK Stark gives you. That's the letter S in the acronym. You also get universality, or Turing completeness, which means that you can generate these proofs and verifiers for literally any statement in computation. Formally, for any language in non-deterministic exponential time, you can verify membership in this language using ZK Stark. Another important property is transparency, which is the letter T in Stark, and it means that when you set up such a Stark system, you don't need to run any ceremonies. There are no trusted parties generating keys. There are no trapdoors in the system. It is fully transparent. All the information that comes from the verifier side is just public random coins. This is especially important if you want the party conducting the proving to be some really, really powerful party that you should have reason to fear or mistrust. So if it's the central bank of some nation state, you might worry whether it's put in any backdoors or things like that. If it's some huge monopoly that is controlling all of your life and it says, I want to prove to you things, you might worry whether it wants to cheat by having backdoors in these keys. So in a ZK Stark, you probably don't have any such ability. So even the most powerful of parties that you can imagine cannot cheat and operate without integrity in a ZK Stark. The last thing which some ZK Starks have, and the ones that we at StarkWare develop, is that you have lean and the cryptographic assumptions that you're based on for the security of the system are basically the existence of some collision-resistant hash function. You're not assuming anything that is a number theoretic. All of your systems are post-quantum secure, and they're also pretty efficient because you use a very efficient cryptographic primitive. Okay, let's go to the next slide. Now, I'm assuming that many of the people joining these this talk are experts in blockchains and also in privacy and cryptography. So you've probably heard of many, many, many different exciting developments. This is a partial list of some zero knowledge and computational integrity proof systems from the past. You have, the Groth 16 system that powers Zcash. You have the Halo, Bulletproofs, Aurora, Ligero, and many, many others. This isn't a full list. And you probably also heard about the very popular acronyms SNARK and STARK. So I just want to say there's a very large set of different protocols. I want to spend a few minutes speaking about what differentiates them and how they are all similar. So let's please move to the next slide. So think of this universe both Stark and Snark are mathematical definitions. And as mathematical definitions go, there are some creatures that have one property, there are some that have the other property, there's some that have both, and some that have neither. So I just want to stress what is the difference in the mathematical definition between a Stark and a Snark, what classes of computations they represent. So for a proof system to be a Stark, it must be scalable according to this very strict definition, in which the proving time is quasi-linear and verification time is polylogarithmic. A Snark does not say much about the proving time. It just, it could be any proving time, but you just want the verification time to be succinct. Another implication of scalability is that in a Stark, you cannot have any linear or any long setup process. It must be very succinct setup. If you're going to generate any keys or anything, they must be very short. Whereas with a Snark, you could have some trusted generator run for a very long time and generate some keys. A Stark must be transparent. There are no trusted setups. There's no private randomness that goes into the system at all. Whereas a Snark insists that the system be non-interactive, and a Stark can or cannot be interactive. So let's move to the next slide. Any Stark can become a Snark, but it's not necessarily the other way around. So hence, Starks are more powerful than Snarks. And I mean, meaning if you constructed a Stark and you really want something that is non-deterministic, then you can apply the Fiat-Shamir heuristic, and then you get a very good kind of Snark that is also transparent and has very efficient proving time and setup time. So again, there's this large class of systems, Starks and Snarks and other creatures which are neither. Let's move to the next slide, please. And all of them share two main themes, and then there are differences in how you implement them. So all of them go through a process of arithmetization that I'll talk about in a minute. And all of them involve some cryptographic way for assuring low degreeness. And the way the different protocols are different from one another are along these two axes: how they enforce low degreeness and how they deal with arithmetization. So let's please move to the next slide. So arithmetization is this beautiful process coming from the field of computational complexity, and it was introduced in the fundamental paper LFKN. So that's Lund, Foltnow, Karloff, and Nissan from '92, where this is in the early days of proof systems. They observed that if you take a statement about computation and you transform it to some other statement about properties of low-degree polynomials, then you get very efficient protocols. And that's exactly what arithmetization is. It takes a computational problem, like, the statement could be, well, there's some 256-bit string Z, and Bob is claiming that he knows a preimage under SHA-2 of Z. That's a very computational statement. And what arithmetization does is it transforms it. Can you please go to the next slide? It transforms it into, let's move to the next slide. It moves it into a different problem that talks about some collection of polynomials. In this case, the reduction would lead to a different statement that says, well, there are these two polynomials. One is multivariate, Q, and the other one is R. And there's some number, a degree bound, a bound on degree of polynomials. And let's please move to the next slide. The claim is not that you know some preimage of Z under SHA-2. The claim is that you know a collection of 4 polynomials that all of them are of degree less than D, such that, and let's call them the polynomials A, B, C, and D, such that if you plug into the various variables of the polynomial Q, you plug in A, B, C, and D, you will get 0 or equivalence. So it's some problem about polynomials. And all of these arithmetization reductions have the same form. They basically prove an if and only thing, an if and only if direction. They say that basically you know a preimage of Z if and only if you know to solve this problem of finding these 4 polynomials. So that's what an arithmetization looks like. And the reason it's useful is that if you do not know a pre-image, and you are forced to work with low-degree polynomials, then the properties of low-degree polynomials, the fact that they are very good error-correcting codes, or the fact that a degree D polynomial has at most D zeros, or the Schwarzschild extension, which says that a multivariate polynomial of degree D, the fraction of inputs that satisfies it is at most D over the domain size. All of these kinds of statements mean that if someone is cheating, is trying to cheat, then if you just check this polynomial relation on a random, uniformly random X, you will see that it does not hold. You will see inequality. And that's the power of arithmetization. It sort of amplifies, it takes any kind of imperfectness, any kind of attempt to cheat and mislead, and amplifies it into something that will be immediately visible if you just randomly inspect this polynomial relation. So as I said, all computational integrity proof systems that are instantiated in practice and used have some form of arithmetization in them. That's one part. Let's please move on. And yeah, let's move to the next slide. Let's move to the next slide. And basically, the second common ancestor, the problem that we have at hand, once we apply this reduction, is how do we know that Bob is supplying us access to 4 polynomials of degree less than D? So we have reduced the problem to a single simple sampling of some random X and checking a polynomial relation. But then we have this very hard problem of enforcing Bob to commit and use some low degree polynomials, and that's low degreeness. So let's move to the next slide. This talks about the differences between the different systems. It is how you do the arithmetization, how you enforce low degreenness, and what cryptographic assumptions you use when you're enforcing low degreenness. So let's move to the next slide, please. So there are 4 general classes of cryptographic assumptions you could use: collision-resistant hashes, elliptic curve, discrete log problem, knowledge of exponent, and groups of unknown order. And the further you move along this axis, the more, the newer the assumption and the less usage it has seen. Just 1 second. It's on. So let's move to the next slide, please. So I just want to say that the same arithmetization method can be used across different cryptographic assumptions and lead to different proof systems, as for instance in the case of Fractal versus Marlin. Let's please move to the next. So in terms of cryptographic assumptions, basically the branch or the tree on which Starks reside assumes only symmetric cryptography, which is also post-quantum secure, whereas all the other systems rely on some sort of number theoretic assumption, and hence they are all breakable by quantum computers in one way or another. So that's one difference between, let's say, Starks and other kinds of snarks. Let's please move to the next slide. So basically, we give the post-quantum security middle to the tree that that resides on the left side. Let's move to the next slide, please. The way you enforce low degreenness, in some cases you use commitment schemes of various forms, and in one particular but very important branch, the one that is used by Zcash and a lot of the snarks and Plonk and these other systems, you are hiding queries to the polynomials, but this requires some trusted setup and also has limited scalability unless you revert to other more advanced techniques like recursion, which are also have their own issues. So let's move please to the next slide. On the other hand, yeah, the next thing is about length of proofs. The ones that use number theoretic assumptions have shorter proofs, and the ones like ours that use only commitment schemes based on collision-resistant hashes have longer proofs. Let's please move to the next slide. And the shortest of the proofs in terms of its byte length resides in this red tree. In particular, Groth 16 is famously less than 200 bytes for a single proof, which is much shorter than anything else. So it gets the first prize in succinctness. Let's please move to the next slide. Another differentiating factor is what is the modulus or the size of the finite field or arithmetic domain in which you conduct your arithmetization. So on the leftmost tree, you can use any field because the field size is unrelated to the security parameters. So you can use fields of size 8 bits or 32 bits and you'll get the same security. You can reach 128-bit security under any field size. As you move to the right, you need large primes for the elliptic curve cryptography, and sometimes you need special pairing-friendly ones. And then if you go to the newest kind of tree, the one that's based on general groups of unknown orders, so you're already in the sort of RSA-safe groups that require sometimes thousands of bits, and this, of course, leads to less efficient computation in terms of time. So let's move to the next slide. So in terms of speed, again, the leftmost tree is the most efficient because it can use any size of field and still have any security level that you wish. Let's please move to the next. The next thing has to do with scalability and transparency. So things that are very efficient are scalable, and transparency we already mentioned. It's the lack of need for any trusted setup ceremony. And here you can see it's a more mixed picture. So let's please move to the next slide. And you see some things are scalable and some of them are transparent. And I gave these prizes to the systems that have transparency in them. Please, let's move to the next slide. And the next, I think this is the last parameter that I want to compare systems across, is how future-proof is the system. So there's the Lindy effect that says that the future life expectancy of some technology is proportional to its current age. So in terms of cryptography, the more your primitive has been in use and the more economic value is based on it, the more likely it will stick around. So let's move on. As you go back and back in time with the cryptographic assumptions, you'll see more usage of them and more value based on them. So if you go to the right, you see only a few blockchain protocols, and then there's some SSL key exchange and handshakes. But at the leftmost, you basically have all of e-commerce needs some form of hash or another. Let's please move to the next slide. And to the next slide. So in terms of economic value, there's a lot more pent on the tree where Starks are. So I have a blog post about this particular topic, and I also did a Stark at Home video about it, so you're welcome. And again, there are going to be hyperlinks in the slides I'll share if you want to learn more about this. But the TLDR, the bottom line is that if you want really, really short individual proofs, then use the Graph 16 snarks. But if you care about anything else, post-quantum security, scalability, transparency, efficiency, future-proofness, you're probably better off working with Starks. Okay, now I want to jump and tell you a little bit about how we're scaling blockchain with Starks in StarkWare. So the basic idea is to take many transactions, these are these red squares, use an off-chain prover to generate one single proof and then submit it to the verifier. So let's please move to the next slide. And then instead of the current system in which each node needs to check each and every transaction, we will transition into, let's move to the next slide, please, a situation where we submit, this off-chain prover submits to all nodes of the network a new proof and a new state. And what the nodes do is they only check the proof, verify the proof, and then they can trust the new state because of the math and cryptography, not because they trust anything about the prover. And this is the basic idea of scalability when using Starks. Now let's see some numbers and what's really happening these days. So StarkWare currently has two product lines in which this technology appears. One is StarkX and the other is StarkNet. Let's talk a little bit about the two. So StarkX, a little bit about StarkWare. So StarkWare currently has something like 60 team members. So far, we've raised upwards of $110 million of funding. By the way, as a little caveat, in a very small number of hours by this evening, if you're following us on Twitter, you'll see that there's some exciting announcements on the funding side, but I'll leave that for Twitter and for later. We're under embargo. Can we please go just one slide back? The main thing we're very proud of is that, we invented a very large part of the stack that we and then others are also using, including, ZK Stark, Fry, the Cairo programming language, Sharp, which is this concept of taking many different programs and submitting a single proof to all of them at once, Validium, which is a mode for conducting data off-chain, and other things. And our mission is to bring scalability and privacy to a blockchain near you. Let's please move to the next slide. Thank you. So here are some numbers. They're a bit not updated. By the way, I'll change. This is as of today, not as of a month ago. So the StarkX system has settled by now over $200 billion of cumulative trading. We've settled more than 50 million transactions across different, 4 different platforms, DYDX, which does perpetual trading, StarkWare, which does fantasy soccer, and just last week, by the way, they announced that the Turkish soccer league is partnering with them. So that's just last week they announced. I don't know if you're soccer lovers and if you like to do fantasy soccer, but StarkWare would be something to look at, which does it on blockchain and sits on our technology. Immutable does NFT minting and trading for gaming and generative art, and Diversify is a spot trading platform. We can pack upwards of 600,000 mints of NFTs inside a single proof. The gas cost per single transaction is less than 500. And this is far lower than any other system, layer 1 or layer 2, that exists out there today. So these are some numbers that show what we've achieved so far, on the ground, on Ethereum for our customers. Let's please move on. And here's just some fun facts. So StarkWare that I just mentioned, before they worked with us, they were spending, around 500 Ether per day, per week, which I think, I don't know, according to Ether price, this was around prices as of yesterday. This was around $2 million per day, current gas prices. Current prices of Ethereum. And with us, they're spending roughly 7 Ether per day. So they reduced the amount of spending while increasing their volume by a very considerable factor. And this is just one example. It is across all of our customers. This is what they see. Let's please move on. Now, so far, I mentioned systems in which other parties have partnered with StarkWare to use systems that we built with them. But the very exciting thing that should open up, it's already in testnet, but will open up for alpha and mainnet within the next 2 weeks, is StarkNet, which is just like Ethereum. It's going to be decentralized, permissionless, a Stark-based rollup. And anyone can write smart contracts and deploy to them. Anyone can submit transactions, and later on, anyone can generate Stark proofs for this and sequence and be the analog of a miner on this system. And this is coming, live alpha in a couple of weeks. So let's talk a little bit about that. So why would you want StarkNet as opposed to, let's say, using Solana or Polygon or some sidechain? So your trust is in math, not in humans. It's not trust in the operators of Solana. It's trust in the resiliency of peer-reviewed cryptographic proofs. And hence, you're also more future-proof. If your assets are sitting there, it's less likely that there will be exit scams, hacks, or government shutdown. Rather, in such systems rather than on a sidechain. Let's please move on. So we already have laid the foundations. The alpha is already on testnet and going live very soon. And on mainnet, later on, we're going to allow basically a lot of applications to interact and compose with each other. That's also going to be on, in the next couple of months. And within the next, I'd say, 6 to 12 months, we'll also move to this latest phase, which is called Universe, in which everything will be decentralized, the sequencing, the provers, the whole system will be Ethereum-like in that sense as well. Let's please move. Okay, so it supports general computation, interactions between layer 1 and layer 2, permissionless deployment of smart contracts and transactions and composability. And very soon we're working with teams like Open Zeppelin and others to have ERC20 contracts and bridges between L1 and L2 and so on and so forth. We have this isn't updated yet. There's a very large ecosystem of teams that are developing. So those of you who do like to write smart contracts or infrastructure and want to deploy on StarkNet or be part of the teams that are building infrastructure for it, please join the Discord group, reach out to me, to our team, to say, here's something we want to do. If you need any help or talk to anyone, we're very happy to help that happen. Let's please move on to the next. If you copy this QR code, you will get to the StarkNet playground. You can also Google StarkNet and StarkNet playground, and you can just start building. There's a playground, there's a very extensive tooling, and testnet is already live. So as I said, the cryptographic technology that we invented and then developed has been embedded into two product lines. One is StarkX that I showed you some numbers about, and the other, which is very exciting as it's permissionless and open to everyone, is StarkNet. It's already something you can work with, and it will go live in alpha mode on mainnet by the end of this month, which is like in the next 10 days or so. Now I want to, in the very last part, do I have time for another, let's say 10 minutes just to, or 5 to 10 minutes to say, again, because this is a academic forum, I want to go a little bit deeper and explain what the process is. Okay.
Please, you can continue as much as you want.
Okay. I think this will be another 5 to 10 minutes, and then I'll just take questions. So let's look a little bit deeper into how you go about generating these proofs of computational integrity. So you start with some statement in mind, and you know, you want to, let's say you say that you checked 10,000 transactions on a system like DYDX, which is a very complicated logic. You need to check price oracles, and if you're liquid enough, and you know, what is the order, and cryptographic signatures and various things, and compute your position. So you want to take that and move it into some system of polynomials that represents the correctness of that computation, some circuit or some constraint system that corresponds to it. And we call it, in the world of Starks, we call it an algebraic intermediate representation. Those familiar with snarks and other systems may have heard of R1CS system, which is rank 1 constraint satisfaction problems. Those are the analogs of our heirs, of our algebraic intermediate representation. Then you want to feed that to some low degree testing protocol. As I said, there are several different kinds. We use one that we built and improved in-house called the Fast Read Solomon IOP of proximity, or FRI. And then you apply basically the Fiat-Shamir heuristic and the Killian reduction and Mikali transformation, things that come from standard cryptography, moving from an abstract interactive oracle proof system to some very concrete argument system, and then you get your Stark. And that's what basically you send to the system. Okay, so let's please move on. Now, the first part depends very much on the CI statement that you have, but the last part does not. It's generic because it's something about low degree testing and then transforming something into a proof that can be verified on chain. Now, the way you do you get your error is basically you want to take the transition function of your computation and view it or capture it by putting certain constraints over some trace of a computation. So here would be some example. So you decide that your trace is going to have 3 columns and, you know, yay many constraints. And okay, let's move to the next slide, please. So it's very, when you get to very complicated computation, it becomes very hard to do. So this is just some screenshot from one of the tools that we developed in-house that, you know, initially when you were dealing in this case with 10 polynomials, and you know, you want to know which constraints are applied to each one of them, then there was some visual tool that lets you look at these constraints. But as you can see, it's very, very hard to understand what's going on and to make sure that that you really capture the correct computation via these constraints. The analogy would be, suppose you want to, you know, program some computation, but you must do it only using wires and NAND gates. So we all know this is possible, but it's just very, very hard for humans to do this directly. And this was the initial state of affairs with the way we built our Starks. So let's move please to the next slide. And then each different computational integrity statement led to a completely different error, and you had to work very hard and make sure that they're all correct and efficient, and this doesn't scale very well. So what we did is invented this one error that has less than 50 constraints. The white paper is already out, and we verified its soundness using the lean automatic prover. And now we have just one set of constraints that captures the transition function of a universal machine, and a pretty efficient one. And now you can, instead of needing to sort of understand what goes on with each and every error, you just have one error to rule them all. And when you want to express a new program, you feed it as input to that error, as part of the input. So we developed also a programming language that, and a whole tool chain for it, and we called it Cairo, standing for CPU error. So Cairo happens to be the first universal von Neumann Stark that has both scalability, universality, and transparency. And it's also the first universal von Neumann architecture with a verifier on blockchain. And it's already been used for a very long time. There are a whole bunch of other, general framework for CPUs and general computation, but this one stands out in being, in these two bullet points that I made here. So as a programming language, we think of it as some, Goldilocks principle. It's not too hot, not too cold. So it has a very simple architecture, only 3 registers, a program counter, an allocation pointer, and a frame pointer. There's a very minimal instruction set, but it also is sufficiently rich to support functions, recursion, branching, conditioning, random access to memory, structures, and a whole bunch of other things. So we think it's quite good at that. It comes with a very extensive tooling, compiler, virtual machine, playground, a whole bunch of other things that you can basically start programming. It is the language in which StarkNet is written and in which all of our StarkX systems are written. So it is already battle proven to be efficient and haul on its shoulders very large and meaningful programs. And with that, I end my part of the presentation. I'll be very happy to answer questions.
Thank you so much for your nice presentation. Any questions from the audience? If you have a question, please raise your hand so that we can unmute your microphone. We can now enable chat screen now. Chat is enabled now. While our audience are thinking their question, maybe I can ask one question. So you mentioned about trace function. So you use a trace, and then maybe there are some block ciphers you use for construction of this trace. So what could be your suggestion for generation of such a trace function? So maybe you use Rindle in your Stark system, or do you suggest another block ciphers?
That's a very good question. Okay, most of the standard ciphers and hashes were constructed optimizing, I don't know, number of gates in silica and these things, and they're very efficient. The AES, SHA-1, SHA-2, Blake. They did not have in mind the question of how efficient is it to prove statements about them using algebra. So these cryptographic primitives are probably, Rindle is an interesting middle case in which it still wanted to optimize silica and electricity consumption. However, for various reasons, they did opt to use the finite field of size 2 to the 8 for various operations. And because of that, Rindle and AES happen to be slightly more efficient if you work over a binary field to deal with. Now, there are some systems that are, some crypto primitives that are provably secure under number theoretic assumptions, and then they are mildly efficient. So one that we are currently using in many of our systems is a Peterson hash, which basically uses elliptic curves and assumes the hardness of the discrete log problem over elliptic curves. And a third class that you mentioned, which is very interesting. So over the past 5 years, there have been a number of suggestions of cryptographic primitives that minimize the number of constraints needed to argue about them in proof systems. So there are MIMC, GMIMC, Poseidon, Rescue, Vision, and this is starting to be a field. Some of these have been started to be in use. I think Poseidon is right now, a lot of people use it. They will lead to proofs that are roughly 10x shorter than the ones that we generate with Poseidon, with Peterson's. And Peterson's are roughly, let's say, 5 to 10x more efficient than arguing about SHA-2 or SHA-3. So basically you have this sort of spectrum. You either go with things that are very standard and secure, but you have very large proofs for them, so you can fit in only a very small number of primitives, or you go with things that are number theoretic and slightly, more secure or have some analysis and some time behind them, like Peterson. So then you go 10x more efficient, or you go with the newest stuff that is even 10x more efficient than that, but its security is just a bit newer. So I don't know, trade-off there. Okay, yeah, I see a question here in the chat. If you want, I can answer it. I can read it and answer it. It says, what is the computational integrity statement, or I guess statement, behind StarkNet? I'll start with this question. Okay, it's a very, very generic statement because it's a statement about some operating system. So think of, okay, let's start with Ethereum. Ethereum has some virtual machine, and each time you you accept a new block, you basically advance the state of that virtual machine, right? The memory, the content of the memory, and you're in a new state. So with StarkNet, the statement being proved is exactly the analog of that. There's some virtual machine with some abstract state, some memory, and each time you submit a proof, you're saying this abstract and universal, Turing complete system has moved to a new state. And because it's a universal machine, you're moving the state of all the programs that are associated with it in each update. So the computational integrity statement is this universal machine, this particular universal machine that was at state A has now moved to state B. That's the statement being proved, that the movement from state A to state B is valid for this virtual machine, universal virtual machine. Okay, the second question. Someone suggested on Twitter that using Verkle trees instead of Merkle trees. What is the point? For some reason, wait a second, maybe I can't read all of it. Just 1 second.
Maybe he's asking, do you suggest Verkle trees instead of Merkle trees?
Okay, so a Verkle tree is basically like a Merkle tree, but where you have a much higher fan-in. And then if it would have been a Merkle tree, whenever you want to say, I'm coming from here, you have to spill out all of the siblings, right? So think of some Merkle tree where the, okay, let's recall first a Merkle tree. So in a binary Merkle tree, if I want to show that going down this path leads me to some element, then for each node in the path, I have to mention one other preimage of, one other part of the preimage of the hash. Now, imagine a Merkle tree with fan-in of, let's say, 256. So it means that in each node, if you want to show that this is a valid move, you have to sort of present 255 other parts of the preimage such that the hash of all of this 256 things is what labels this next node. Okay, so if you do that, you get a tree that has much lower depth, but the witness length just becomes larger. So the point in a Verkle tree is to use some proof to replace displaying all of those 255 preimages. So you would just prove, I know using some proof, snark, a Stark, a Plonk, whatever. I know of 255 preimages such that with this one thing would have led to the output there. And it's an interesting trade-off. And so currently in our systems, we're not using it. We're better off just using simple Merkle trees. But in some other systems, I think it's being explored. You're computing such a Merkle tree is much more, takes much more time, but updating it in certain cases is more efficient. It's a reasonable option to use in certain settings.
So some of our audience was asking that how are fees paid by end users on StarkNet?
Right, so that's a very terrific question. They're going to be paid. So in the very beginning, no fees are going to be paid, but that's very temporary. That's mostly for technical reasons till we get all the infrastructure up for dealing with fees. It's going to be pretty much like on Ethereum. There'll be some gas-like metric that now incorporates. Hopefully, the whole purpose is that the overall price that you'll pay is significantly lower than on layer one. Otherwise, we've done nothing. But it still will be the amount you're paying will be somehow proportional to the amount of resources that you're consuming. So those resources will be your L1 footprint, because sometimes you're going to use StarkNet to also do things on layer one. Some of it is going to be things like storage on layer two, and some of it is going to be computation on layer two. And you'll pay for all of these. So it's going to be Ethereum-like. Hopefully, the fee is going to be much lower. And like in Ethereum, it's likely going to be determined by some market, free market mechanism with a simple pricing. So it could be a first price auction, which means when you submit, you're invited to submit your gas limit and things like that. And if it's sufficiently good, then some sequencer is going to take it.
I would like to ask one more mathematical question still, if you accept. You were working on AG codes, algebraic geometric codes, and transitive, which has somehow automorphism group, which is transitive, even two transitive. So is this still are you still looking for such kind of automorphism, such kind of AG codes, or did you see that there can be such kind of a good construction? We know that it is proved by Henning that could be built on tower of function field, but do you believe that one can prove explicit such a AG code?
Okay, so we use those AG codes that you're referring to, which are really magical constructions that have asymptotically good. They're asymptotically good codes. They have constant alphabet size, constant rate, and constant relative distance. And the magical part there was that they have transitive automorphism group. So we use them in one of our earlier works to get more efficient PCPs, which are very much related to Starks. That line of research is still extremely interesting. Some of the interesting questions there are, you would like an encoding function that is very fast, FFT like quasi-linear time. We don't care, at least in the context of our proof systems, we don't really care that much about efficient decoding, erasure decoding, or from random errors or for anything, because in the context of proofs, all we care about is the honest prover, and the honest prover is just going to use the correct encoding. But we do care about finding an efficient basis for that, and an efficient encoding algorithm for that thing. Now, I'm not saying I don't necessarily know whether, suppose tomorrow there's this super efficient transitive AG code. I'm not sure that, let's say, StarkWare or someone else is going to use that in their constructions. I mean, there are many, many, many considerations that go into such a thing. Not the least of is just being compatible with things that already exist. And, by the time we, even if it is theoretically more efficient, there's all this infrastructure that has been built, and just moving it around and redoing things could be a significant undertaking. But from an academic point of view and a research point of view, this is a terrific open question. And related, I just want to say that in this context, it's interesting, even like, it's very, very nice to have an asymptotically good code that does all of these things. But it would be perfectly fine if you get a code that is, much better than Reed-Solomon. It is not provably asymptotically good, but nevertheless, practically speaking, it is whatever, twice better than, or 10 times better than Reed-Solomon, and has an encoding algorithm that is just as efficient, or very close to being as efficient. This would already be tremendously interesting for us. And I want to mention in this context that we half a year ago published a paper that is somewhat related to this. We showed how you can take basically how you can do FFTs, just like efficient low degree extension and Reed-Solomon encoding, even when your field is not FFT friendly, when it doesn't have any subgroup of size 2 to the k. And you can use, instead of some subgroups that are native to the field, you will use subgroups that are on some elliptic curve over that field. And because you have much more variability in the size of the elliptic curve groups in the Hasselwell bound, you get more freedom there. So that's just one example of something that says, now a code over an elliptic curve is by no means close to the to the Iwara constant. It's not even a tower. It has genus 1. It's not good as an asymptotically good AG code, but it could be useful for us because, for instance, you can do much more. You can do arithmetization much more easily over native fields, even if they are, for instance, safe primes. So a safe prime means that p minus 1 is basically 2 times some other prime. So there are no meaningful multiplicative groups, but for 2 and some other crazy prime. So it's not FFT friendly, but using an AG code, an elliptic curve over such a safe prime that it may have FFT friendly structures, and we could use that. So that's one example of one direction that uses AG.
Thank you. Setap Hocam, you raise your hand.
So I have 2 questions. The very first one is that I see 2 figures on your board, on your back figure. Are they the famous Alice and Bob in? I'm not from this branch. I'm from actuarial science area. So I heard about the Bob and Alice. They are 2 important figures. I just wanted to know if they are, because I meet them now.
Let them be Alice and Bob. The true answer is that before that, at a certain time, the screen was completely blank. And because of that, my camera had a problem focusing. So I just needed something there to be drawn. And I just drew these 2 things. And yeah, let them be Alice and Bob. Why not?
Okay. My second question is about when the dimension increases, do you consider the probabilistic likelihoods? What are the chances or the probability of demolishing the security, or in the forward or the backward in the chain system? I mean, I hope that's not a very silly question, but is it a kind of consideration? I just want to clarify.
Yeah. So okay, I hid under the rug all discussion of probability, but probability is really, really crucial to all of cryptography and to all of the field of interactive proof systems. I didn't say this, but really, if you think of a classical proof from logic, the one that is taught in Mathematical Logic 101, so it has perfect completeness and perfect soundness, meaning a statement, a theorem is in the theory, if and only if there exists a string such that that string is the proof that ends with a theorem, and there's no probability involved. However, you get no privacy and you get no scalability. There's no ability to check succinctly such a proof. You have to go through all of it. Now, when we move to zero-knowledge proofs, when we move to scalable proofs where the verification is much shorter, then we must pay with something. Mathematically, this can be proven. You must pay with something. And what you pay with is you pay with interaction. Now you need a back and forth. and you need randomness, and you incur a probability of error. And you cannot get them away. If you would get them away, this would go back to first order, logic or propositional calculus, and then you get no efficiency. So probability is a very, very important. In fact, if you look at any paper on IOPs, on probabilistically checkable proofs, on interactive proofs, always the hardest part is bounding the probability of error when the statement is incorrect. That is the hardest part. That is where all of the mathematical thinking and ingenuity goes into. It's called the soundness error, and understanding it has been really the bread and butter of people in proof systems. I mean, interactive proof systems and PCP theory for the past 40 years. So it's a terrific question. It is the one aspect that is most interesting, and from a mathematical point of view, the most ingenious concepts that go into the PCP theorem, into IOPs, Starks, and so on, are related to understanding and bounding the probability of error.
Okay, thank you. That was a very, very nice talk. It was opening the horizon. I guess I will leave to Oğuz, but I guess it's going to be the end of our nice seminar. Oğuz?
I would like to first thank Professor Eli Ben-Sasson for giving us this nice presentation, and all our participants to come and join this nice seminar. Hope to you week on 13th of November, I think. 2 weeks later we have a new seminar. Hope to meet there again.
Thank you. I would love that, and I will send the slides, and you can share them, and you can also share the video. That's also fine. Thank you very much, Professors Yela and Kestel, and everyone who attended. Thank you.
Thank you. It was one of the most participated seminars, so that's really a great success for us too. Thanks a lot for you.
Thank you. Okay. Bye.